Welcome back. In this video lecture, we will discuss about the applications of Laplace and Poisson's equations, which we have learned in the last video lecture. We have already come across the dielectric mediums, the polarization, and also the boundary conditions at the interface of dielectrics. And also in the last SLT lecture, we have discussed about what actually are the Poisson's and Laplace equations. Now in this video lecture, we will see how they can be employed to determine the potentials. I hope that by the completion of this lecture, you will be able to apply Laplace and Poisson's equations to determine potentials. Now, let's come back to the problem. We will do a problem today. See, the question states that a uniform voltage distribution, a uniform volume charge distribution of minus 10 to the power of minus 8 coulombs per meter cube occupies a region between two coaxial cylinders of radii 20 and 50 mm. If the electric field and potential are both 0 on the inner cylinder, find the potential on the outer cylinder. Which means that there are two cylinders which are having a common axis. Okay, the radius of which is 20 mm and the outer cylinder it is 50 mm. Now, he says that on the inner cylinder V is 0 and E is 0, and he says that there is a volume charge distribution in this region, interregion, between these two cylinders, and this volume charge distribution is rho V is equal to minus 10 to the power of minus 8 coulomb per meter, and he wants to determine the potential on the outer cylinder. This is what the question states. See, there is a volume charge distribution occupying a region between, so this is the region between two coaxial cylinders, and its value is this one. The inner radius is 20 mm, outer radius is 50 mm. And he states that electric field and potential are both 0 on the inner cylinder. That is what I have written here. And he wants to determine the potential on the outer cylinder. So this is the question. So now we will try to apply Poisson's equation to this particular problem. So it seems that two cylinders, the region between these two cylinders has a volume charge distribution. So we will start applying the Poisson's equation. We know that the Poisson's equation, this is the Poisson's equation, right? Del square V is equal to minus rho V by epsilon. So we'll try to apply this particular equation now. Okay. Now if you see, the given configurations are basically of cylindrical configurations. So I'll try to apply cylindrical coordinate system. So this related to cylindrical coordinate system, we will try to apply the same. You know that in the last class itself, we have tried to employ this particular one. If it is cylindrical coordinate system, what is the expression? So this is the expression, right, for del square V, isn't it? So I'll write it here one more time, 1 by r dou by dou r again dou by dou r of V plus 1 by r square dou square V by dou pi square plus dou square z by, dou square V by dou z square. This is my del square V, which is equal to minus rho V by epsilon. So this equation we will try to solve now for determining the potential on the outer cylinder. And when I am applying this one, if you carefully see, he says that he is considering the entire cylinder and he is not considering any concept of z. So I'll ignore the values of phi and z and I'll assume that only this component is present. Okay, I'll assume that the fields are being extended only onto the lateral surface region. So I'll consider only this component, ignoring the other two components now. So only the radius is assumed to be varying or significant. So I'll ignore the other two components. So what I'll be getting only this r component. Okay, so this is my expression now. This is my new modified Poisson's equation, which is applicable to this particular configuration. And in this one, if you carefully see, this value is already given for you. Rho v, it is given as minus 10 to the power of 8 coulomb per meter cube. And epsilon is also a constant. It is absolute permittivity, you know that. And since no medium has been given, I'll take epsilon of r as 1. And epsilon, you know the value, 8.85 to 10 to the power of minus 12. Right? So these values are already known and it is just a constant. So the variable values are r and v. So we'll try to solve this particular equation. So first of all, I'll try to send this equation, this 1 by r to this side. So what it will become? This 1 by r, it will get multiplied here. So this is a constant. So now what I'll do is nothing but I'll try to integrate this particular one. If I integrate, see, I am trying to integrating with respect to r. So if I integrate this with respect to r, what I will get? This one will go. So this is only will be remaining. And here, since this is constant, for r, what is the integration? R square by 2 plus indefinite integration. So I am taking a constant c1, which will be helpful for us at the later stages, right? So this is my new equation. Again, if you carefully see, there is again one more r. Again, I will shift this one to this side. So what I will get if I shift to this one? This will become r by 2 and this will become c1 by r. So this is my equation. Again, I will integrate it with respect to r in order to obtain the potential. So again, integrating, what I will get? See what I will be getting here. If I integrate it again, here I will be getting v. This one, it is constant, right? For r, what is the integral? It is r square by 2 plus this is c1. 1 by r integral is ln of r, right? So this is my expression, minus rho v, v is equal to plus constant over there, right? By 4 epsilon r square plus c1 ln r plus c2. This is my expression for voltage. Now I don't know the values of c1 and c2 actually. Yeah. I don't know the values of c1 and c2 and I'll apply the conditions which have been given for it. See, in the question it has already been mentioned that the electric field and the electric field and potential are both 0 on the inner cylinder. So which means that for inner cylinder r is equal to 20 centimeters, v is equal to 0 and e is equal to 0. So I will employ these conditions to determine c1 and c2. Later on I will determine the potential on outer cylinder. So two equations have been given to determine two unknowns. So we will try to solve that one. First of all, I will go with E is equal to 0. We will try that one. So applying that electric field on inner cylinder is 0. Inner cylinder means R is equal to 20 millimeters, which is nothing but 0.02 meters. So this is the expression for V, right? So if you want E, what you should do minus del V. You know the del gradient of V in cylindrical coordinates. This is a gradient, isn't it? But there are, sorry, here plus must be there. But there are no these components. I do have only this particular component. So what I will do is nothing but I will differentiate it with respect to R. So if I differentiate it with respect to R, so this only term I will be considering now. So if I differentiate it with respect to R, so what I will be getting here? See, E bar is equal to, if I differentiate it with respect to R, this is constant, right? R square, what I will be getting? 2R plus C1, this will become 1 by R plus 0, isn't it? Into UR bar. Let us consider only the magnitude now. So what I will be getting? E is equal to minus rho V by 2 epsilon R plus C1 by R. This is my expression for magnitude of electric field intensity. Yeah, see here. This is my expression. So if I substitute, I don't substitute the values of these values, I will substitute them at the end. It will make me easier because these are of 10 to the power of minus 8 and 10 to the power of minus 12. It is a little bit clumsy, right? So you leave this one, you substitute the remaining values. R value you substitute. What is R value? Inner cylinder, so it is 0.02. I will substitute this one, 0.02 by 2 minus C1 by 0.02. So E is already given as 0. So if you solve this one, what you will be getting? So C1 by 0.02 is equal to rho V by epsilon 0.02 by 2. So which means that C1 is equal to rho V by epsilon 0.0002. Right, or 0.0004, but this is my C1 value. I have already obtained one expression. Now I'll apply the second one, which means potential is also 0. So if I apply that potential is already 0, this is my expression. I know already the value of C1. What is the value of C1? Right? This is the value of V. Now, yeah. Now what he is saying, potential is 0 on inner cylinder. Sorry. For inner cylinder, R is 20 mm. This is 0.00 mm. Yeah. So if I substitute it here, V is 0, R value is 0.02. If I substitute here, what I'll be getting? I'll be getting the value of C2. See, this is the value of C2. Now I do have values of C1 and C2. C1 value I have obtained, C2 value I have obtained. So I know this is C1 value and this entire thing is C2 value, which we have tried in the earlier case. Now I am substituting these values. Apart, I want potential on outer cylinder, right? So V is equal to, for outer cylinder it is 50, right? 50 mm. Okay. So I will substitute the value of R as 0.05. So R square, this is the value. R value I am substituting it here. C1 I am substituting, C2 I am substituting. If I solve this one, this is my expression. Now I know the values of rho V and epsilon also. Epsilon is, I am taking it as 8. So epsilon R becomes 1. So epsilon naught value is this one. And rho V value is this one. So substitute these things, you will be getting the voltage of minus 0.386. If I am wrong, please correct them. Now, this is the way how we employ Poisson's equations to determine the potentials. I hope that you are now able to apply Laplace and Poisson's equations to determine potentials. Thank you. And this is a take-home problem. Try to solve this problem at home and come back with the solution. Thank you.